Hi, I'm Troy Magennis, and I often get called upon to do lunch and learns. And this one is about agile data and forecasting that I gave recently, and I'm recording so that everyone else can get access to it. I love data, and this is lovely data. I mean, look at it. It's the weather data, wind direction, speed, and precipitation by sort of location and longitude and latitude. It's fantastic stuff, but it's pretty inaccessible. And even with these millions of points, what can we do with it? We could turn it into something lovely to begin with. I mean, look at this. This is a website called Windy, which takes those same observational text data that you just saw and turns it into something that you can admire and understand. In actual cases, a lot of pilots have said for the first time they've really understood weather, wind direction and speed at certain elevations and so forth. And it can even forecast. You can drag the slider along the bottom across and see what the weather may be at some time in the future. A great way to do a forecast. But I'm going to pose a question to you. So even with billions of historical data points, do we always get a reliable forecast? Is it always what we expected? And I think we've all lived long enough to realize that weather forecasts are directionally correct, but often locally wrong. And that's what I want to talk about today. Why do why does even having a billion historical data points still mean we can't reliably forecast? So think about something that's maybe closer to you, travel time by car, plane, or bus. When we used to do such things, we used to commute to work and so forth. Do we always get our travel time right? Even though we've done it many, many times, if we're commuting to work or on a plane trip and so forth, maybe rarer, but a bus trip, we might take a bus every day at regular intervals. Even with many historical samples, are we able to accurately predict travel time? Now, what data gives us, historical data gives us, is an expectation about what is more likely to be true, but it doesn't account for specifics of any one trip. So it is directionally correct, but not specific in any circumstance. And what we call this is context. Historical data gives us a forecast without context. And that's what we need to consider when we're actually setting out to forecast in another field like software development. So if you think about software estimates for how long it's going to take to build a piece of software or how long it's going to take to design a bit of hardware, if we've done it a lot before and it's similar to what we've done before, we can get pretty close. But if it's something brand new, if the context is different, it doesn't really work. So when we're asking developers and product designers to give us an estimate about what they're doing, we've got to realize that they're basing it on their historical data that they have seen, and it's going to be directionally correct as long as the context hasn't changed. Context, context, context. Now, often what happens with the way we set out to do forecasting and estimating in the software world, at least, is we remove any context and we try and dumb it down to just being a straight extrapolation of historical data. And that's where we're going to get it wrong. Why do we get it wrong? Well, there's a couple of reasons there as well, not just that we ignore context. It's a big one, but not the only one. Here are the three I mostly see. And fourth, because why not? We're off by one errors, we're in software after all. First of all, we wish it to be so. Secondly, is the historical data that we have is no longer valid for a particular varying reasons. I'm going to go into each of these three throughout the rest of this deck. And sometimes the work is dissimilar to anything we've done prior, but mostly we do other stuff instead. And that's not always a bad thing. If we're able to, the whole idea of Agile is that we can spend our effort where it's most needed at that time. So what I want you to think about here is, you know, how can we get through these three top reasons of why we get it wrong? And how can we encourage people to understand the value of choosing to do other stuff if it's more important when we find out about it? So let's go through the first reason we get our forecast wrong. We wish it's so, and it doesn't come true. Well, it turns out our brains are a little bit more complex than we expected, but they're simplistic enough when they get overloaded with data that they take shortcuts, and we call these shortcuts cognitive biases. And this is a lovely diagram of all the different types of cognitive biases that our human brains are susceptible to. You know, we don't we can't remember everything. Sometimes we get flooded with too much information at one time. Sometimes there's a speed imperative and we don't have time to do the analysis that we need to do. And sometimes we're not quite certain what we're looking at and we can't really decide how to act upon. And mostly what happens is when we ask a developer or a team to estimate and forecast, we flood them with information. We give them too much information and they have to try and work out which information to combine and understand. And our go-to knee-jerk reaction when we're flooded with information is we draw from details that confirm our existing beliefs. In other words, we don't try and analyze it too deeply. We sort of say, you know, I think it should be X and it's likely to be X, so it's X. And it's this, we've got to understand that the psychology of when we ask people to estimate and forecast hard things, that they're going to get it wrong. And we've also got to recognize on the receiving side that when we get told information, we have to run a barometer over that of how could they know that? Do they have enough information to understand that? Have I told them where the real effort and value lies? I bet there's room for improvement on both sides. So as Frederick Heigl said, we learn from history that we do not learn from history, right? I mean, we've done estimates and forecasts for many, many years in software development, and we're still getting it wrong on a daily basis and sort of saying maybe just a little bit more estimation would help. And that's not always true because if we use our experience alone, our personal experience, we could be wrong due to cognitive bias. And as I said earlier, if we use historical data alone, we could be wrong due to context. And there's nothing, wrong with each of these. We just got to find a balance between the two. We've got to use enough data to overcome our biases, and we got to, understand that our data is fallible because of lack of context. So wishing it so isn't going to cause it to be true, and we've always got to use a bit of data to fight cognitive bias and a little bit of cognitive bias to fight just relying on data alone. So back to our why do we get it wrong? That was number one. We wish it so, and our brains take shortcuts. But now let's look at number two. Our historical data isn't valid for some particular reason. I'm going to pose a question. Who can estimate or forecast their travel time best out of these two groups of people? All right, now, if you're sort of saying the smug bicyclist in the yellow shirt, why he doesn't travel as fast when he's on open road as what the cars and motorcycles could, who look very sad and are stuck in traffic. But because he has movement and flow, he can extrapolate better how long it's going to take to do something. And those on the right depend, they do not understand because they have no flow at the moment. They might have had flow prior when they were driving at non-peak hour travel times. But right now, that peak hour travel time data is irrelevant. It doesn't matter. And, utilization changes sort of velocity. So what the biggest context you want to look at about historical data is, are there any patterns in it that mean that utilization changes and that will change velocity of travel, whether that be in software development or so forth. I mean, and it's not about having a faster car or a better team or a 10x team or a slightly better process. If you're in a congested system where those high value assets can't travel at their normal speed, you cannot forecast or predict when anything's going to be done. So perhaps one of the biggest things about using historical data is to understand when it was captured, what was the congestion or the blocking issues in the system at that time. And we have a way of understanding this. I mean, we all sort of have this intuitive concept of when things get busier, any one thing gets slowed down. So this is sort of known as sort of the queuing time, utilization versus queuing time. And what we're looking at here is how quickly, as utilization grows, so utilization is on the horizontal axis there, along the bottom here. As utilization grows, the amount of time that any one item has to wait, queue, for its ability to be serviced by someone grows exponentially above a certain point. And where is that point? Well, it turns out that point is around controlled by a variable called variability. And if everything, the arrival time, if the arrival time of the work is spread out over 24 hours, then that variability of arrival time is sort of smoothed out and we can service things when they arrive. Think about if you go grocery shopping, if you have to wait the queuing time versus the serving time grows very large because there's not enough servers to check out people to process your funds. So what changes how much utilization there is in the system is how much variability there is in the work itself, in the size of the work that it has to be, and the arrival time of that work. So if you can control arrival time and you can sort of reduce variability of the service time, the working time of solving it, then you can move into higher amounts of utilization. But that does not describe software development in any way, shape, or form. We think that we have to run at high levels of utilization, and we plan to high levels of utilization to begin with, and that's valid, but only if you can control the arrival time and the variability of the cycle time of doing that work once we do get to it. Now, the way we do that in Agile is we try and reduce work in progress, which means that we've controlled the arrival time. And by reducing the work in progress and sort of constraining it so that we do one thing at a time and we focus on it, we actually decrease the variability of the cycle time if that work is similar to work we've done before. So Agile has a scientific reason for having WIP limits and for understanding and managing cycle time and getting the work that we start done as quickly as possible and then moving on to the next thing. And as we sort of move up the variability, you sort of see that at a certain point, and it's going to be around about sort of 80%, 1 in 5, it starts, the time waiting for any piece of work to start exceeds the time it's going to take to do the work. And it just goes pear-shaped from there. Now, I'm not saying that you shouldn't plan for capacity that you have, but I think that you must control the arrival rate of that work to the team once you've planned it. And the reason you're doing that is you pay a huge price for not managing that arrival time into the teams. So to get your forecast better, you've actually got to set better limits of the amount of work in progress and enable the team to finish the work that it started rather than start new work. And I can put a sort of dollar value on this, and I'll put the links in the video description and so forth. But I have a lot of these little interactive articles where you can drag the sliders, and it will actually put a dollar value on how much time and price you're paying for that planning of an extra 5% of the utilization of the team, or not managing the system variability of the arrival time and so forth. And you will be stunned at just how many more times expensive it is to actually have a team congested in high utilization than it is to manage that utilization to a reasonable level and actually get a lot more work through. And this is not an uncommon equation. I see where the cost of doing work would be $5,000 based on the cost of not having that work delivered at a moment in time, the revenue lost and so forth. But the queuing time of waiting to get started on that piece of work is at $23,000. And, it's 4 to 5 times is not uncommon for what we're paying for the queuing time. And I put a dollar value on that, but we also put the inability to forecast through. Just like the bicyclists and the people in the traffic that you saw, and the motorcycles and the cars, we spend a lot of money on the cars and motorcycles, and then we have them sitting idle in a very congested system. And that makes it almost impossible for us to forecast and estimate how long anything's going to take because they're all stuck in that congested traffic. Can't forecast if there is no flow. So let me pose to you the question: how do you put a system into overload? And there's sort of two ways we currently do that. We take on too much work, or we have too few people to do the work. And it's not the number of people we have. There's only one point in a delivery system that matters. So we have too few people at a constraint. It's like having a 13-lane highway go down to 1 lane. It doesn't matter how good the road and the traffic flow is on the 13-lane highway if they all have to merge through a work site to go into 1 lane. All right. So what we really need to understand in our systems in order to forecast and understand whether we've put it into overload is where's the constraint? And it's adding people at the constraint that matters, or adding capacity at the constraint, or making sure that the constraint is only working on the one thing that we want them to work on. And it's a very complex sort of situation to do. But I'm posing a question to you. Does adding more people work? I mean, even if we could add more people at the constraint, do we actually see what we're expecting to see? And there's an equation for this. This is something called Amdahl's law, and you're not really sort of going to believe the severity of this, but it's true. And this is math, and it's not new math, it's old math. This comes around from the 70s and the 80s when we actually knew, how to understand. If we could throw more people at a problem, or more processes at a problem, and do more work in parallel, would that improve the throughput of the system? And with one person, okay, this is two inputs. Again, the link to this sort of calculator is going to be in the description. If we look at the number of people or teams that we have there, I've got that set to 1, and that team, it makes no sense at the moment, but this is the amount of work that can be done in parallel before there has to be any synchronization of that work or any integration of that work in the software world. Okay, so you understand, if we got one person and they can work 80% of the time in parallel, then they end up 1 times better. Okay, but what if I sort of increase the number of people to 5? How much more improvement am I going to get by going from one team or one person at the constraint to 5 people at the constraint? Well, let's sort of run Amdahl's formula. And you sort of see that at 5 people, we only get throughput improvement through the system of 2.78 times, which isn't the 5 people we're paying. We're only getting about, roughly half of what we're adding in cost there to the system. But what if I had 1,000 people or teams doing the same work? What would that improvement be based on Amdahl's law? Have a think about that. 1,000 people. I'm going to give you the budget to go and hire 1,000 10x developers or 10x testers or 10x product managers. What is the improvement going to be down here? At the moment, it's 2.78 for 5 people. Less than 5 times. We actually pay a huge cost improvement, and we think that we're solving the problem of the constraint, but we don't. Because unless at the constraint those people can work independently without having to merge their work or collaborate or sit in sort of coordination meetings to understand how their work accumulates into the whole delivery, you don't get a lot of improvement. So adding people really isn't the solution in most cases, because when you move especially if often the way we increase resources quickly is we move people around. So we borrow them from another team. We take the testers from team A and we move them to team B because they're something that we see as urgent to get done. Now you're paying twice, right? You've moved all those people out of the other team who you're going to put them into a high constraint, a high utilization situation because you've taken team people out. You put them onto team B, and they're not really going to improve the performance much at all anyway, right? So you actually pay twice, and it's not like this is new. We knew this from the beginning of time. We knew this from the Mythical Man Month, which is I think in the 70s, that adding people, the Mythical Man Month doesn't actually, it makes work slower. It makes you deliver slower, not faster. And again, how you're paying, the losing team gets into high utilization, which equals standstill. And the gaining team, they fix one constraint, but there's probably another constraint in their system somewhere else. And often the constraint we have when we bring people across is you gotta bring those new, excuse me, you gotta bring the new people into the team and train them up. And they take capacity away while they're doing that. So moving people around is a bad thing. And another point I want to add there, and this drives me insane, is often we bring in external people to do new work. Don't do that. Bring in people externally to take over work that you're currently doing that's well known, and bring the people from the teams that you have to do new work. Why do you do that? Why is that beneficial? It's because the existing people that you had, A, they learn a new skill, so they're more likely to stick around because they're being challenged. But secondly, they can train the new people coming in on the old task. And they bring the context of understanding the organization into using the new skills, the new frameworks or the new techniques, and you get a better product at the end of the day because these existing staff understand the customer better than they do. So if you are going to add people, add them elsewhere and bring your internal staff up to speed with the new skills while they train and help out the new staff you've hired on the old skills. So I see that done badly. I see a lot of the time there's a new framework or a new technology, and what we do is we bring in consultants and we give them the new work, and then hence what's built doesn't stick with the company and knowledge doesn't stay with the company. And secondly, the people you had doing the old work, they're going to leave because they're unchallenged. Don't do that. All right. Now, another thing I want to talk about is that there is how we do naive forecasting using historical data to begin with. And this is ubiquitously, universally done poorly. And I'm going to run you through this. Say we have three features, a triangle, a circle, and a heart. Now, when we set the teams or a group of people the task of estimating the work, they take those features and they do a rough analysis of them to estimate how many stories or how many pieces of work there are in delivering those features. And you see feature triangle there comes down to 3 stories, and feature circle comes down to 1 story. It doesn't split at all. And feature 3, the love heart, the yellow, comes down to 2 stories, 2 pieces of work. And we estimate those and we sum up the number of stories there is in each of those features to do the piece of work. And then we divide it by the rate, our historical throughput, our historical velocity. Don't do that. Because when the teams actually get to implementing the work, often what they have to do is split that work further to the size that makes sense to develop, whether that be based on dependencies or whether that just be based on it's not all going to fit into one sprint or period of time. So all of a sudden, those 3 stories of the 3 triangles become 6. And the 1 big circle story that was estimated becomes 2. And the 2 love heart estimated stories become 4. Now our throughput and velocity numbers that we use for calculating and dividing against are measured at a throughput of 12, but we've actually only delivered 6 of the original things that we estimated. So if you take a backlog of story counts or story points, however you roll, I don't really care what it is, but we divide that by a measured throughput or velocity rate that's after a team has split that work into smaller pieces, and we don't account for that splitting, we're setting our teams up for disaster because it looks like we're delivering twice as fast as what we are. And it's between 2 to 3 times universally I see. Now, this is the rule. Never use a done column throughput and velocity to divide a backlog column. You can't do that. The math doesn't work out. One is in miles per hour and one is in kilometers per hour. Now, I'm not saying that splitting work is the wrong thing. In fact, it is essential. You must allow your developers and your teams to split the work into the right size that they have for coding and developing, or getting the AI to code and develop nowadays, right? That has to be done in a certain size. But you just can't use that same number for forecasting. And, on my epitaph on my grave is going to be, he was good with spreadsheets. I have a whole heap of spreadsheets where what I do is I ask you, what do you reckon that work is going to split with between the backlog column and the done column? You should have a bit of an intuition of your own, and it's easy to do, right? Just tag the same feature that when you start it, give it the same, a common tag in Jira or GitHub Issues or whatever you use, and just compare what it was at the beginning to what it was at the end. And you really don't have to be exact there, but it's almost never going to be one unless it's just repetitive toil work. And it could be as high as 3 to 5 times if it's a significantly complex piece of work. And they're both right. They're both good. They're both what was needed. But all I'm saying is you must account for it in your forecasting. And it's easy to do. Just understand what your split rate is. If you use my spreadsheets or my multicolor spreadsheets, it's automatically accounted for you. Other than that, then double your backlog size or halve your throughput size. I don't care which one you do, but it's going to be roughly in that order of magnitude if you haven't done any measurement. And now start paying attention. Splitting's not bad, just needs to be accounted for. All right, so back to our little agenda of why do we get it wrong. That's how historical data becomes not valid. I just gave you a couple of 3 or 4 sort of different reasons there. And number 3, now, work is dissimilar to anything that we've done before. And this is a good thing, right? I mean, we can't expect that our teams are going to continue to do similar or the same work as what they do. The more innovative we get, the more that changes. So, it might be really easy for your teams to estimate and forecast accurately how long it would take you to change the year on the copyright footer of the homepage. All right, that's something that has low complexity. Most developers can imagine what they need to do if they've done it before in that organization. There's normally going to be some approval process or some. That aside, it's low complexity, pretty easy to implement. But how long would it take you to build a custom LLM to classify how people feel? I mean, we went for many years not really having LLMs at all, and now we've got LLMs, but there's still only 3 or 4. There's a reason why the people who invent new LLMs are getting paid a very large sum of money at the moment. It's because it's still a unique skill and it's still a little bit hard. And that hardness is the fact that we don't really know until we've done it how long it's going to take to do it. And, it works like this. First of all, everyone knows how to do a piece of work, an idea of something that we're looking at. Everyone. So it's likely to be able to be estimated and forecast with a similar or a good degree of accuracy. Someone on the team knows how to do it. I just don't, but someone on the team does. I can ask them. Someone in the company knows how to do it, but they're not on our team, so I need to go and ask them what they think and so forth. Someone in the world knows how to do this. Remember, that's the pre-LLMs and post-LLMs. Now we know that there are people we can hire and give us advice on how long it takes to do a new LLM. Well, there's no one has done this yet in the world. And just think about the continuum. When we ask teams to estimate and forecast features, there's a blend of all these complexities in our backlog. So if there's one thing that you need to really understand in order to understand the reliability of your forecasts and estimates that your team or company is going to come up with, it's this context. Back to the beginning. It's this context which plays a very key role in determining what estimates and forecasts are going to be useful. Now, I have a spreadsheet out there which helps you put multiple features in a list, multiple estimates of points of velocity, and what it gives you is just whether it's going to make a certain target date or not. And it gives you a green tick for yeah, you're good, a red X for no way, and a little yellow ampersand there. Sorry, yeah, exclamation point to tell you that it's on the line. And if you look at the inputs, I have start date, target date, likelihood. This is a probabilistic forecast, so it's sort of I want to be 85% sure. The splitting, I talked about that earlier, the low and the high guess. Our throughput and velocity historicals, whether you use estimates and a worst case and a best case, whether the team is focused on this work, the features, their estimates, the scope complexity. Now I'm going to ask you, which of those inputs do you think plays, or I've seen, plays the biggest role in forecasting errors? Have a think. All right, lock it in. What do you think is the biggest factor that causes poor forecasts? Start date. And start dates are terrible, right? If you see a start date that's aligned with a quarter or a month, it's wrong. It sort of tends to be thrown in there as a starting point of where we expect work to be started. Has it started? Has the team rolled off on the other prior work that they're doing? Has something more important not come along? If you can get one input and ask questions about one input, make it the start date. Have a definition of what started means and write it down. And if that hasn't been hit yet, the forecast is not going to be accurate. And it seems like a seemingly innocent input, but it is one of the biggest factors that you need to account for. Number two, have a think about what my number two is going to be. Yep, you get it. Very few things you could do with estimating the work down here shoddily can be swamped by a 1 to 2x growth of that work just based on bad data management, bad mathematics, dividing a throughput or velocity after work is split with a estimate of the number of stories it's going to be pre-split. So that's going to be 1 to 2 times, 1 to 3 times, depending on how complex your work is. Number three, what do you think number three is? It's whether the team is focusing on this work. Now, when we get teams to estimate and forecast one feature at a time, their mindset is, if we as a team work on this feature at that time, this is what we could do it. And the same thing with throughput and velocity. If you're using the entire throughput of velocity and applying it to this amount of work, when the team or half the team is off doing production support or finishing off a prior feature or having to sit in forecasting and estimating sessions of future work, you cannot assign the entire throughput estimate to this work. Now, what should you default it to? Well, if the team is working on the most urgent thing in the company and there's broad agreement of that, then this might be higher than 50 to 75%. I don't really ever put it more than 80%. And I'm often sort of loath to go above 50% because there's often half the team doing other stuff. And it's not half the team doing other stuff, it's half the people or the skill set you have at the constraint doing other stuff. So again, you've got to understand where the constraint is in your team and the system with the type of work you're doing. And this number, this 50%, is how much of that capacity you have allocated to this work. It's hard. We think it's simple, it's hard. Then the next one I find there is the one I just mentioned before, is not understanding the scope complexity of it. It doesn't matter how good your estimates are on points of velocity if you cannot get the team to state whether they understand what you're talking about, whether they don't really understand what you're talking about, or whether it's really unclear and they've got a vague idea of what you're doing. And often when we say, oh, just give us a swag, I got this idea for this feature, or we want to go out and build this new LLM that does a machine learning algorithm to understand whether our customers are left or right-handed. Put yourself in the team's perspective there. They either have to spend a large amount of mental time trying to understand that problem and what the gotchas are in implementing it versus changing the copyright on the footer. So don't expect every feature that you're going to forecast to have a similar complexity profile. That's absurd and it's not right. If you're just doing, I'm not saying have everything clear and understood, because the amount of work to get to clear and understood prematurely when it may not even be shipped is a waste of time and money. But understand which ones fit into which category, and then understand that the forecast you're getting is more or less likely to follow the historical data based on this complexity. This is your cue for context, is that there's unknown context which are going to cause us problems with this feature. So get the team to spend more time saying where they currently are in each of these complexity groupings for each feature, more than getting them to break down where it's an 8 or 20 point story or that sort of planning poker stuff. It's just not, it's not even in my list yet. What's next? So that's 4 of them. What's the 5th one? Still not the estimates. It now comes down to the special cases of throughput through a year is bumpy. I've seen some companies which do an annual conference where they're out there, the whole company stands still for a month and a half. Well, they stand still for 2 months. 1 month preparing for the conference, then doing the conference, and then 1 month recovering from the conference, because there's often a lot of feedback you get when you meet with your customers en masse like that, right? In some countries, they shut down for periods of the month, different months. In Europe, August is almost a dead zone. In the Southern Hemisphere, Australia, and so forth, December and January are very dead times because people take vacation time. And not all people, just people at the constraint. It doesn't matter how many people around them, support staff around them, if they're not at the constraint, it's not going to impact flow. But often these key points of the year, you're losing people across your organization at a constraint. Remember, constraints move around. You've got to know where it is at any point in time. I do not find that the historical data of estimates of throughput and matter more than maybe 5 to 10% of the errors. And I don't really find that the story point estimates matter as much as these other 5 factors. So it's this context that will make your weather forecast better or your software estimates and forecasts better. Understanding the stuff, the peripheral values which affect throughput and affect whether whether the estimates we can even come up with are valid and the start date, that matter most of all. So that is my very sort of cautionary tale for understanding what you should look at, just beyond the obvious of throughput and velocity and the story counts or story points for estimates. They matter, but not as much as you think, and they won't matter if the work is even remotely complex or the team doesn't have focus on the work, or they're in a situation where their done column throughput and velocity is artificially high based on the fact that they have to split that work into smaller chunks to code it. Again, that's good value. Everyone has to split the work. You just can't ignore it when you're doing your mathematical calculations on velocity. So again, I'm Troy Magennis. You can contact me at troymagennis@focusobjective.com. I love doing these lunch and learns. So if you're interested, just reach out. I also do training and workshops internally where I get product teams and dev teams together to practice communicating uncertainty and estimates and all that context I spoke about. But thank you for your time.